So our next step is to find the partial derivative of our cost function with respect to some weight from some neuron U to some neuron V in layer L-1. That is, if you have a neuron U here and a neuron V here, we'd like to consider how the cost function changes when you change the weight of the edge going from U to V. That is W of UV L-1. So just as last time, let's redraw our tree diagram, which aided us in applying the chain rule to the cost function. The cost function was a function of the activations at the output layer L, and the activations in and of themselves were functions of the weighted inputs at the respective neurons at output layer L. And then we tag along the differentiating variable. And this is something we do for any variable. If we were differentiating with respect to some arbitrary variable x, we'd include x here. But here we're differentiating with respect to the weight uv L-1. And then applying the chain rule, we get that the partial derivative of c with respect to this weight is the sum from I goes from 1 to n of the partial derivative of c with respect to the activation at some arbitrary neuron in the output layer times the derivative. And remember, this was not a partial derivative, as the activation is a single variable function of the weighted input. So this is the derivative of the activation at neuron I with respect to the weighted input. And then we multiply that by the partial derivative of the weighted input, which again, we go back to writing a partial derivative as the weighted input was a multivariable function of weights and biases. So this would be the weighted input at neuron I with respect to the weight going from U to V in layer L-1. So now our goal is to break this expression down further. Let's write it there. This is partial derivative of the weighted input at I with respect to the weight from U to V at layer L-1. So if we just break out the weighted input term in terms of its linear combination, we get the sum from j is equal to y to n, and I'm using j as an indexing variable as I already used I in the outermost summation. But here I get the weight from j to I at layer L multiplied by the activation of the jth neuron in the previous layer plus the bias term at the ith neuron at the output layer. Because remember, we're considering the weighted input of neuron I at the output layer. Now distributing this derivative, we get sum from j is equal to 1 to n of the partial derivative with respect to the weight for this product Vji L A J L-1 plus the partial derivative of the weight with respect to the bias term. And so if we look at our diagram, what we're doing here is we're asking how does the bias term, which we add to the ith neuron in the output layer, how does that change when we change this weight? And as we'd argued earlier, it doesn't, because these are network parameters which we choose ourselves. Us setting one value for this weight has no bearing on what we set here. So this bias term doesn't vary with our weight, so this just cancels to 0, and we're left with this expression right here. So here we essentially have to ask, if we vary this weight right here, is it going to affect any weight going from layer L-1 to layer L, which is what this term is? And the answer is once again no, because they're network parameters which we set ourselves. The value we input here does not have to affect the value we choose for this weight right here, which will be the weight from neuron 1 to neuron 1 in layer L. The next question is, does this weight, this WUV, does it affect the activations at layer L-1, that is, following activations? And the answer is yes, it affects the activation at neuron V, as we can see here. If I 100x this weight, it's going to change the output of this neuron. But it's not going to affect the output at the nth neuron, because this weight is not incident to n, and it's not incident to the first neuron. So seeing as this weight term not being a derivative of the weight from u to v of L-1, we can put it outside of the differentiation and get the sum from j equals 1 to n of w ji of L multiplied by the partial derivative of the activation at neuron j with respect to the weight from u to v of L-1. Now we have to further break down this derivative right here, which we can do here. And as we saw on our graph, our weight only affects the activation of the VF neuron at L-1, which means that the derivative of an activation in any other node with respect to WUV is 0. So the only activation that actually gets affected is the one at neuron V. When j is equal to v, only then do we get a non-zero term, which is the derivative of the activation at v at layer L-1 with respect to our weight. Otherwise, we get 0. Now we can break this derivative down further, which we can do here. So this derivative, once again, AV at layer L-1 would be a function of the weighted input at neuron V at L-1. So here I'm just utilizing a tree diagram, which we can use to employ the chain rule. And then, of course, we add differentiating variable at the end. And so following along this one branch, we get that the derivative of the activation at neuron V with respect to the weighted input. And once again, this is a regular derivative as the activation is a single variable function of ZV. And we multiply that by the partial derivative of ZV, which is once again weighted inputs are a multivariable functions. So we're once again going back to a partial derivative of ZV with respect to UV L-1. Now let's examine this derivative right here. We get that the derivative of CV, the weighted input at neuron V, with respect to our weight uv is equal to the derivative of our weight uv, L minus 1, and then unpacking the linear combination which the weighted input consists of, we get the sum from k. I'm using k as a summation variable here because I've already used j and I in outer summations. So here I get the summation from k is equal to 1 to n. And since I'm always running n here, it essentially means I'm assuming that in my neural net, all the layers have the same number of neurons, which they don't have to have, but it sort of simplifies the notation a bit. So here I get the weight from k to neuron v at layer L minus 1 multiplied by the activation of some arbitrary neuron k in the layer before that, which is layer L minus 2. And then we add a bias term at the v neuron at layer L minus 1. This linear combination becomes our weighted input at neuron v. Now we have to ask ourselves, if we're at neuron v here, and we have some bias term, which we add to our neuron v, and we have activations at the previous layer, we have to ask ourselves, which quantities does our weight affect? Does this weight affect the activations from layer L minus 2? No, it doesn't, because our weight lies ahead of the activations. The activations at layer L minus 2 are affected by weights and biases in layers prior to layer L minus 2. And we have to ask ourselves once again, does this weight affect the bias term at neuron v? No, it doesn't, because the weights and biases are network parameters which we set ourselves. Now finally, we also ask ourselves, does this weight affect an edge going from layer L minus 2 to layer L minus 1? And it doesn't affect this particular edge, for instance, the edge which would be from neuron N in layer L minus 2 to neuron V in layer L minus 1. And it wouldn't affect really any other edge outside of itself. So changing this variable would affect the edge value as we're changing it directly, we're changing itself, but it wouldn't affect any other weight, as once again, those are separate network parameters. So if we go back to our expression and we consider which quantities change with respect to this weight, the bias term disappears, as we've seen previously, and we're left with a sum from k is equal to 1 to n. We stated previously that activations from the previous layer, from layer L minus 2, are not affected by the weight going to layer L minus 1 and therefore lying ahead of the activations. So we can take this activation term and put it outside of our derivative, and then we're left with this derivative right here, the derivative of some arbitrary weight from some arbitrary neuron k in layer L minus 2 to neuron v in layer L minus 1 with respect to our weight. And once again, breaking this down further, this weight does not affect any of the weights going from layer L minus 2 to layer L minus 1, except for the weight itself, which means that when k is equal to u, we get the following derivative, uv, the derivative of weight uv with respect to itself, which is just 1, and this is the case when k is equal to u, and when k is not equal to u, we get the partial derivative of some other weight going from layer L minus 2 to layer L minus 1 with respect to our weight going from neuron U in L minus 2 to neuron V in L minus 1, which is just 0. So this is when k is not equal to u.